Okay. So last class we were discussing this formulation in formulation in natural coordinate space. So we started with this isoparametric formulation. So we had discussed here that in this formulation what we do is we want to have arbitrary quadrilateral in physical coordinate space so that we can take care of arbitrary geometries. So we have x, y, and these are the nodes in the. So this is what when you take a structure, you are discretizing the structure in the physical coordinate space. But as far as the development of element level governing equations are concerned, because we assume the approximate solution in terms of natural coordinates. So the formulation is done in natural coordinates for solving this problem in physical domain. So when you use a software and you create the geometry, lines, surfaces, and volumes, you will discretize that in the physical space. But then each element is mapped to a natural coordinate master element in the natural coordinate space, which is square. So that is what we said, that no, this element in the physical coordinate space, which is having nodal coordinates as x1, y1, etc., x2, y2, x3, y3, and x4, y4. So this is mapped to a square in the natural coordinate space. So actual structure you are not discretizing in the natural coordinate space, in the physical coordinate space, but in the formulation you are using this. So this is the element 1, 2, 3, and 4. So we had discussed this. Minus 1 are the coordinates, and 1 and minus 1, 1 comma 1, and minus 1 comma 1. So these are the coordinates. So the element now, the depending on whether it is a heat conduction problem or a plane stress plane strain problem, you will interpolate the the variables in terms of the unknown variables in terms of the natural coordinates xi and eta. So that is what we have discussed in the last class. And what you are doing is, if any point p is there whose coordinates are x and y in the physical coordinate space, that point p is mapped to a point with coordinates xi eta in the natural coordinates. So there is one to one correspondence between the points in the physical coordinate space and the natural coordinate space. And of course we develop the shape functions and so on. So we what I had said was in the last class that we interpolate the temperature in terms of the shape functions, which are functions of natural coordinates. So ni into ti, where I going from 1 to 4. But now we also need to relate the x, y, and xi eta, because we need the derivative of no temperature with respect to x and y, and also the integration has to be done over the physical coordinate space, so in the physical domain. So we also interpolate the x and y. So I had said that this is going from 1 to n nixi, and since it's isoparametric formulation, we use the same shape function for interpolating the geometry, that is xy, and also the unknown variable, in this case temperature. So we are doing this from 1 to 4, not n. So you have ni into yi. So where we had defined the shape functions, of course, so that you can have a look at in your notes. So we had said that n1 is nothing but 1 by 4, 1 minus xi, 1 minus eta, and n2 is the shape function corresponding to node number 2, which is 1 plus xi, 1 minus eta, 1 by 4, and n3 was 1 by 4, 1 plus xi into 1 plus eta, and n4 was 1 by 4, 1 minus xi to 1 plus eta. So these were the shape functions. So in a nutshell, this is what we discussed in the last class. And I had said, no, in terms of, I also introduced the concept of Jacobian matrix. So I am just summarizing what we did in the last class, not in detail. So that we also set the Jacobian matrix. So we said the Jacobian matrix is given by del x by del xi, del y by del xi. So you see that no, through this relationship, x is expressed in terms of, because xi and y are the known nodal coordinates. So ultimately x would be function of xi and eta through this relationship, because ni's are functions of xi and eta. Similarly, y will be function of xi and eta, and they are explicit functions of xi and eta, so you can differentiate them with respect to xi and eta and get the Jacobian matrix. So we had this del x by del xi, del y by del xi, then del x by del eta, and del y by del eta. So this was the Jacobian matrix, and then the inverse of this Jacobian matrix, J inverse. No, that is the inverse of the same thing, del x by del xi, del y by del xi, del x. So you can actually differentiate this with respect to xi eta, get define the Jacobian matrix, and then find its inverse. So its inverse, we said that, let us say it is J11 star, J12 star, J21 star, and J22 star. You have to calculate this J11 star, J12 star, J21 star, and J22 star by, from this inverse matrix. And then we had said that the derivative operator relationship was that del by del x was J11 star del by del xi plus J12 star into del by del eta. So from this you will be able to calculate the shape function of any derivative with respect to x, and using this operator relationship, del by del y is equal to J21 star into del by del xi plus J22 star into del by del eta, we will be able to calculate the derivatives with respect to y coordinate. So we had defined this. So this is where we are, the last class. Now let's continue the same problem. So next is the development of element level governing equations for the same 2D heat conduction problem which we have discussed. So now let me start with that. So element level governing equation for the same 2D heat conduction problem, and then of course we will also do the plane stress plane strain problem to the 2D heat conduction. So for this we had already from the differential equation we had got the integral functional, so which was half, and of course in most of the cases I am developing the element level governing equations from the integral functional, but you can also develop them directly from the big form, the way I illustrated for one of the one dimensional problems. So this was k, and then we had del t by del x and del t by del y transpose into del t by del x. These are the temperature gradients, del t by del y. So you have to of course make a note between x and xi, eta. So this is x, this is h dx dy. That's the first term in the integral functional. Then from the heat source inside that, so we had this T transpose. So let me just write as only T transpose. So we had T transpose into Qg into h dx dy. So this integral functional we have used even for the triangular element we have used. So this is same, and then minus integration over boundary of the element, and then we have T transpose into Qn h into ds. So this is what now we have. Now in this case we have already discussed for the four noded isoparametric element, the temperature T is written in terms of the shape functions. So the four shape functions we have already defined, n1, n2, n3 and n4, and into the temperature value which are at nodes T1, T2, T3 and T4e. These are the values of temperature at the node points. So now this as usual we call this as T equal to H interpolation matrix into vector of elemental degrees of freedom. So this is H and this is D. And then we also need know the temperature gradients. So if you look at del T by del X and del T by del Y, so because the shape functions derivative as I said in the last class that explicit derivatives you can get with respect to xi and eta, and then using these relations you can get the derivatives of shape function with respect to x and y. So let us say at a particular xi and eta, we have calculated the derivatives of the shape functions with respect to x and y. Then we can write these temperature gradients as del n1 by del x, del n2 by del x, del n3 by del x, and del n4 by del x, and similarly del n1 by del y, the y derivatives, del n2 by del y, del n3 by del y, and del n4 by del y into the temperature values at the node points, so T2e, T3e, and T4e. So this is what now we call as B into DE, the temperature gradient matrix. So this matrix is B and E. We are using the same notation what we have been doing so far. And then now you get the element level equations from delta I equal to 0. So the approach is same. I'm not repeating. So you will get that as this KE into DE. So this form of the equations is same, although their explicit expressions would be different. So that is F external plus F internal. Now let me define here. So the all the matrices. So where now if you look at this Ke is the integration over area of the element, and then you have this K, and then you get here B transpose into B into H into dx into dy. But now you will have to realize that the shape functions n1, n2, n3, n4 are expressed in terms of xi and eta, the natural coordinates. So their derivatives, del n1 by del x, del n1 by del y, and so on, will also be functions of xi and eta. So then this integral has to be converted. The integration with respect to xy has to be converted in terms of integral with respect to xi and eta. So this integration, because now in the physical natural coordinate space, the xi and eta are varying from -1 to +1, but the integration we want ultimately over the known physical coordinate space, because this is what we want to evaluate. But since b is a function, b transpose and b are functions of xi and eta, so we cannot explicitly evaluate this integral with respect to x and y. So we need to convert this integral with respect to xi and eta. So that is what it actually means, is that if you look at this mapping from natural coordinate space to from physical coordinate space to natural coordinate space. So if you take this element x, y, and the same nodes 1, 2, 3, and 4, and there is a corresponding mapping 1, 2, 3, 4, the same logic. So if you take any element here of length d xi d eta, so if this area you take in the natural coordinate space, so this area is going to be d xi into d eta, a differential area, and that area would correspond to, in the physical coordinate space, that would be some area like this, and this area then would be equal to, I proof I'm not giving, this will be equal to determinant of the Jacobian matrix. So the two vertical lines are denoting the determinant would be equal to j times determinant of j times d xi d eta. So therefore from this expression we can write this ke, no the now the no we can write dx dy. I mean integration, it's not really dx dy we are writing as determinant j d xi d eta, but we are saying that area over the physical coordinate space is equivalent to the area over the natural j determinant j times d xi d eta, that is the integration over the natural coordinate space. And in the natural coordinate space, the xi and eta coordinates are varying from -1 to +1. So then the integration limits become -1 to +1, -1 to +1, and this remains same. And anyway, B transpose and B are functions of xi and eta. So the integrand is a function of xi and eta. You have h, and in place of dx dy, we are writing determinant j times d xi d eta. So you can write the integration like this. So you would see that the integration becomes standard always for all the elements. It would be from -1 to +1, -1 to +1, because all the elements would be mapped to the same element which is square in the natural coordinate space. So this integral becomes actually standard integral. And then of course if you look at the external load vector, so which is, f external is integration over again area of the element, and then we have h transpose into qg into h into dx dy. And with the same logic, we convert this integral into natural coordinate space. So integration becomes -1 to +1, -1 to +1. H is already in terms of shape functions, and the shape functions are in terms of xi and eta. So the integrand is already function of xi and eta. So qg into h into determinant of Jacobian matrix j into dx dy. Jacobian matrix we have already defined. So this is basically determinant of the Jacobian matrix, determinant J. So you can write f external in an integral like this in the natural coordinate formulation. And of course your f internal, which is involving the boundary integral, so that would be same. Of course, so when you evaluate for a given problem, you have to carry out the integration ultimately in terms of the one of the natural coordinates, because you would be moving along one of the boundaries. So this would be integration over the boundary, and we have h transpose into qn h into ds, where s is the path coordinate. And here you will find the determinant of j is the way we have defined the Jacobian matrix. So if you look at this j here, so this is the Jacobian matrix. Its determinant would be this into this minus this into this. So the determinant of the Jacobian matrix is basically uh, del x by del xi into del y by del eta minus del x by del eta into del y by del xi. So this is the determinant of Jacobian matrix J. So now once we have done this element formulation, so the other steps, that is discretizing a problem, for given coordinates, xy coordinates, you have to evaluate the element level conductance matrix, external load vector, internal load vector, and then you have to basically assemble all the elements, impose the boundary condition, and solve the problem. So that part really remains same. So now before I actually move on to further, now this integration, as far as the integration over natural coordinate space xi and eta is concerned, so rather than explicitly integrating, what that means is that we multiply, get first the derivatives of the shape function in terms of xi and eta, then multiply b transpose b, and then integrate each term explicitly. Rather than doing that, actually, a standard practice is that we evaluate these integrals numerically. And in finite element, what is most popular numerical integration scheme for evaluation of these stiffness matrix load vector is Gauss quadrature numerical integration scheme. So before I start that, I just wanted to discuss that what would be j. Suppose how to evaluate, of course, j, then its derivative, and then inverse of the j, and then the derivatives of the shape functions with respect to xi and eta, that you should be able to do, and then the derivatives of shape functions with respect to x and y. So I'll just demonstrate for one case that how this j is a very important quantity here, the Jacobian matrix, because that is coming in the derivatives of the shape functions. So let me, if I have an element which is a rectangle in the physical coordinate space, so J for a rectangular, this is actually an example how to calculate Jacobian matrix. So J for rectangular element is rectangle in physical coordinate space. Physical coordinate space means xy, that is xy space. So then what I am actually meaning is that we have the element, although no, the formulation is valid for any arbitrary quadrilateral as we said, but let us say the element is a rectangle in the physical coordinate, and these are the coordinates and the nodes are 1, 2, 3, and 4. And please know, you ask, if you have any question in between, so you should ask the questions. So now you have 1, 2, 3, 4, these coordinates, nodes of the element, and the coordinates are, let us say, x1 and y1 is the first node. But since the element is a rectangle, so this side length is a, and let us say this side length is b. So the coordinates of node 2 would be x1 comma a into no y1, because y coordinate is same, and the coordinates of 3 would be x1 plus a and y1 plus b, and the coordinates of node 4 would be x1 and y1 plus b. These would be the xy coordinate. Of course, the temperature values would be same, no, say T1, T2, T3, and T4. And then this is mapped to an again the square in the natural coordinate space. So you have xi and eta, and these are the nodes 1, 2, 3, and 4. You will also sometimes, suppose you are given a point in the xy coordinate space, and you want to find out the corresponding point in the xi eta coordinate space, then you will have to solve those equations. So that is another point I wanted to make over here, is that you have this. So you see that x is explicitly expressed in terms of xi and eta, y is explicitly expressed in terms of xi and eta. If you are given x and y, then by solving these equations, you should be able to find out xi and eta. So if for the simple rectangular element in physical coordinate space, the relationship is straightforward, it's linear. But no, if the element is arbitrary quadrilateral in the physical coordinate space, then you have to solve the nonlinear equation to find out xi and eta. And why you would be interested in doing that? Because say the temperature or unknown displacements are interpolated in terms of xi and eta. So we want to find them out at some point here, at some point P with coordinates xy. First thing I have to do is, corresponding to this xy, I have to find xi eta, and once I find out xi and eta, then I can get the shape functions at that point, all the ni's and their derivatives, and then I can calculate that variable and its derivatives with respect to x and y at that given point. So that is you should be able to actually do that. So now if you look at x is equal to the formula is same, that is ni xi, and I going from 1 to 4. So now you will see that the x coordinate of, so in the summation, if you look at, we will have basically n1 into x1 and plus n2 into x1 plus a, and plus no n3 into x1 plus a, and plus we will have n4 into x1. No, these are the coordinates I am substituting. So now what you can do is, you can write this as n1 plus n4, these together into x1, and this one you can write x1 plus a into n2 plus n3. So you can write it like this. Now if you look at the shape functions, so you will find that n1 is, if you remember the shape functions, so I have written, so if you look at n1 plus n4, yeah, so I have written the shape functions here. So if you look at this n1 plus n4, so in this you can take 1 minus xi actually common, 1 by 4, 1 minus xi common, and then inside you will have 1 minus eta plus 1 minus eta. So eta will cancel, you will get actually 2. So you will get 1 by 2, 1 minus xi. So what you will get is, here n1 plus n4 you will get as 1 by 2, 1 minus xi into x1. And similarly, if you look at n2 plus n3, so that would come out as 1 by 2 into 1 plus xi, and of course this x1 plus a remains there. Of course, if the values of x1, x2, x3, x4 are given, so you have to put, and of course you simplify these expressions, you finally get the expression for x and y. So therefore x and y, let me take the constant terms together. So we can write this as 2x1 plus a. So that is here, a 1x1, another x1 plus a from here, that is a constant term, divided by 2, and plus you will have a by 2 into xi. So this is now the x in terms of xi. So suppose you are given a particular value of x, so even you would be able to write, no, so from this if you want, you can also write xi in terms of x. So you will find that xi in terms of x would be 2 upon a, and then into inside we will have x minus 2x1 plus a divided by 2. This minus is for the whole term. So this will be expression for xi. No, for the arbitrary rectangular quadrilateral elements, this relationship is going to be complex. So usually we use a Newton-Raphson method to solve for xi and eta if we know a particular x and y. And the starting initial guess for xi and eta would be usually 0, 0. So similarly, if you look at y for this rectangular element, this is not for any element. This is only for this specifically when I am saying the element in the physical coordinate space is a rectangle with the dimensions a and b, and so these are the coordinates. So therefore similarly if you look at y, so that is going to be y1 in no n1 into y1 plus n2 into y2, n1 into y1 plus n2 into y2 is nothing but equal to y1 plus n3 into y1 plus b plus n4 into y1 plus b, because y4 y3 is y1 plus b and y4 is also y1 plus b. So now if similarly if you do n1 plus n2, so you will find that that will come out as, no, you can take 1 minus 1 by 4 1 minus eta common, and inside you will get 1 plus xi plus 1 minus xi. So xi will cancel, you will get 2, so you will get ultimately 1 upon 2 1 minus eta into y1. And similarly if you look at this n3 plus n4, you would be able to take out again 1 by 4 1 plus eta common, and then when you look at the inside term it would be 2, so you'll get y1 plus b by 2 into 1 plus eta. And if you now similarly take the constant terms together, so you get 2y1 plus b divided by 2 plus b by 2 into eta. So this is the expression for y. And now from this if you want to get you can also write eta would be nothing but 2 upon b and then y minus 2y1 plus b whole divided by 2. So this would be eta in terms of y. So if we know y, for particularly for the post processing, we would be interested in finding out the quantities, the variables and their derivatives at given xy location. So first we have to find out the corresponding xi and eta coordinates, and once we know the xi and eta coordinates, then we can calculate the shape functions at that point, and then using the nodal values we can calculate the variable at that point through summation, like in this case summation and iti are their gradients. So now if you want to look at j, the Jacobian matrix for this case, so j by definition is del x by del xi, del y by del xi, del x by del eta, and del y by del eta. So now if you look at del x by del xi, so this is the expression for x. So if we differentiate it with respect to xi, we will get a by 2. It's a partial derivative. So we will get here a by 2. Now if you next term is del y by del xi, but y is only function in this case only. You keep in mind that this is only for the rectangular case. For arbitrary quadrilateral, x and y will be functions of both xi and eta. But only in this case you find that y is only function of eta. So del y by del xi would be 0. Similarly, del x by del eta would be 0, and as you see, del y by del eta would be b by 2. So the Jacobian matrix is simply a by 2, b by 2. So if you look at its determinant, so the determinant of the Jacobian matrix is simply going to be ab by 4. That is going to be the determinant. And if you look at the inverse of the Jacobian matrix here, J inverse. So J inverse, how do we calculate? So we divide the 1 upon J, and this is a 2 by 2 matrix. So basically we interchange the diagonal elements, so we will have b by 2 here, and of course this is done in terms of adjoint matrix, and the sign of the half diagonal elements is changed, but they are 0, so b remains 0. So if now determine j is ab by 4, so if you take it inside, so you will see that this will come as 2 upon a 0, 0 and 2 upon b. So that means the J inverse is basically 2 upon a 0, 2, 0 and 2 upon B. So you can say that in as per our notation J11 star is 2 upon a, J12 star is nothing but 0, J21 star is 0 and J22 star is 2 by B. The way we have already done the calculations. So now if you wanted to know in for this particular case for the rectangular element, if you want the derivatives of the shape functions with respect to x and y, so if I have any shape function ni, so you would see that del ni by del x would be equal to j11 star into del ni by del zeta. So j11 star is 2 upon a and del ni by del xi, and plus we have j12 star into del ni by del eta, but j12 star is 0, so we only have this term, and then you get del ni by del y similarly will be equal to j21 star into del ni by del xi, which is j21 star is 0, so that term goes to 0, and then j22 star into del ni by del eta, so we get 2 bar b into del ni by del eta. So from this we will be able to calculate the derivatives of all the shape functions with respect to x and y, and because they are already explicitly expressed in terms of xi and eta, so these derivatives you can directly get. Yeah, so now so I was talking about, so this is just I wanted to give an example that how do we calculate the Jacobian matrix and then its inverse and the derivatives of the shape functions. So this is now the next thing I want to talk about is the numerical integration. So now so far whatever we have been doing the element level governing equations, ultimately the matrices we were deriving by doing the explicit integration. But for arbitrary quadrilateral and 2D and 3D problems, that is not really many a times either very involved or not possible. So we evaluate those using numerical integration. So now I want to talk about this Gauss quadrature numerical integration. Although there are other numerical integration schemes, but this is with lesser number of calculations, you actually evaluate the matrices accurately. So this is what is used in finite elements, and so we call it as Gauss quadrature numerical integration. So first let me demonstrate a simple thing, that suppose we have an integral from -1 to +1, and the integrand is a function of xi, which is f xi. This integration we want to do from the integration of this f xi from -1 to +1. So in the numerical integration, now what we do is we convert this integration into a summation. So in the summation, what I am saying is that let us say we have know the variable I, so the number of points where we explicitly evaluate the function is n, so I going from 1 to n, and then we evaluate the function at xi I into we multiply the some weight factor. So we are converting this integral into summation. So of course, when you would have studied the first time the integration, so you would have been taught that basically, the integration is nothing but a limiting case of summation. So now we are doing the reverse. That no, we are converting the this integral as a summation. So what we are having two things. This is the value of f at point xi, and into we are multiplying wi. So it is kind of in place of d xi you are taking wi, and the function of course f is evaluated at that point. We can also say that no, the f is high I is nothing but the value of function f at I, so we can call it as fi. So we will have I equal to 1 to n fi into wi, so you can write it like this. So here this point, look, no point high I, these are the the specific points. So these are known as the Gauss points, so now the integration points, we call them as either simply Gauss points or the integration points. So Gauss points are integration points. Because why integration points? Because uh, by evaluating the function at these points we are carrying out the integration, so we call also these as integration points. And the wi is known as weight factor, so these are weight factors. So in place of these high we are taking these weight factors. So this is how we basically in the numerical integration, this is how we evaluate the integral. Of course I will take some, and why I am saying teaching this, because this numerical integration is used to evaluate the element level the coefficient matrix and the load vector, etc. So that is why we are studying this. So now one important question you may ask, sir, how do we choose this capital N, the number? This is n is not safe function, this is no the number of Gauss points. So here n is known as the number of Gauss points. Number of Gauss points are integration points. Sometimes we say Gauss, or sometimes we say no, both are same. Gauss are integration points. So the next question arises, how do we choose n? So how to choose n? So I'm not going to give you the proof of whatever I'm doing over here. So let us say that if the integrand, which is a function of xi, is a polynomial, and that polynomial is of this form: a0 plus a1 xi plus a2 xi square. It is nothing to do with the approximate solution. I'm just saying that we have some function and which is a polynomial, and a0 up to am are known constants, so am into xi to the power m. So if we have this kind of a function, then we take n. The n is taken as basically approximately taken as m plus 1 by 2. So sometimes when you do this m plus 1 by 2, it may come out as a fraction, so we approximate it to next integer. So that is, this is approximated to next integer. So this is how we choose n. And depending on n, we need to know what are the values of xi n and wi. So we need that. So these are available, there are subroutines available, the derivations are there to get this. So suppose if I have n is equal to 1, so then there is only one Gauss point. So the location of that Gauss point would be at xi equal to 0, and the corresponding weight factor w1 would be equal to 2. But suppose if I use n equal to 2, then there, because summation is going from 1 to 2, so we will have xi 1 and xi 2. So in this case xi 1 is basically minus 1 upon root 3, and corresponding weight factor w1 is 1, and xi 2 is equal to plus 1 upon root 3, plus 1 upon root 3, and the corresponding weight factor is 1. And suppose we choose n equal to 3 Gauss points, then there has to be 3 values of xi and the corresponding weight factors. So in this, xi1 is basically minus 3 upon square root of minus 3 upon 5. The corresponding weight factor is 5 by 9. So these are the values one needs to use when you are carrying out the integration. Xi2 for this case is 0, and the weight factor w2 is 8 by 9, and then xi 3 is plus 3 root 3 upon 5, and the corresponding weight factor w3 is 5 by 9. So no, these are the various shape functions. No, sorry, the various weight factor. No, the Gauss points for one point integration. So if we use capital N equal to 1, that is known as 1 point integration. If you use capital N equal to 2, it is known as 2 point integration. If it use capital N equal to 3, then it is known as 3 point integration for 1D case. And of course in 2D we will be discussing how to do this. So now let me take some examples on this numerical integration. So example 1 is, let us say we have to carry out this integration -1 to +1, and we have no the simple function 2 plus 3 into xi. We want to integrate it from -1 to +1, and we want to do it numerically. Of course explicitly you can do, because simple integral. So if you want to explicitly do this, so then it would be first term would be 2 xi, and the second term would be 3 upon 2 xi square, and then the limits would be -1 to +1. So if you put the limits, the second term would be actually 0, so we will only get this as 4. But we want to evaluate this numerically. So we will now, if you first, we need to decide capital N. So you see here m, the highest power of this xi is 1, so m equal to 1. So therefore n would be equal to m plus 1 by 2. So that would be actually 1. So that means this integral I, so if I call that as integral I, so integral I can be evaluated as, now because summation I going from 1 to n, and n value of n is only 1, and then we have no fi into wi. So since I is equal to only 1, so we will have f1 into w1, and f1 means value of f at xi1, and actually xi1 is 0, so the value of function is 2 plus 3 into 0 into w1 is 2, so you get it as 4. So you will see from the numerical integration we get this as exact value. So you see this is exact integral. So numerically also we are able to get the same thing what we get explicitly. But yeah, of course, this is a very trivial example to demonstrate the numerical integration. But when it comes to the finite element matrices and vectors, they are quite involved. So the numerical integration becomes much easier. And now let me take, now if we just take more number of points, then what happens? So now I have just said that minimum requirement of number of Gauss points is 1 for this case. But suppose if we take, no, for the same thing, if we take say n is equal to 2, then what would be, I will be I going from 1 to 2, and then you have fi into wi. And so that means the function is evaluated at first location. So 3 into xi1 into w1 plus 2 plus 3, you will have, you are summing it over all the Gauss points. So 2 plus 3 into xi2 into w2, and you put the values. We have already, for 2 point integration, we have given the values of xi1 and xi2 as plus minus 1 upon root 3. So the first term would become 2, and because xi1 is minus 1 upon root 3, so we will get minus 3 upon root 3. w1 is 1 plus now 2 plus 3, and xi2 is 1 upon root 3, so we get 1 upon root 3. w2 is also 1. That is what I have listed over here. No, for 2 point integration, xi1 is minus 1 upon root 3, xi2 is plus 1 upon root 3, w1 is 1, and w2 is also 1. So now if you sum this, again you get 4. So what it means is that, no, if you use the number of points more than what is minimum required, then also you get basically the no exact value of the integral. Of course, if you use the lesser than the minimum points, then you will under integrate. So in this case, of course, the minimum, the minimum number of points we need is only n equal to 1, so we cannot go less than that. So that's what we can do. Now let me take a second example. So it's the same thing I just modified. Then let us say we want to evaluate this integral I, which is -1 to +1, 2 plus 3 xi, and plus, let us say we have 4 xi square. So I'm adding one more term, d xi. You want to evaluate this integral, and now if you want to exactly evaluate this integral, you can do that. So I know first term would be 2 xi plus 3 xi square by 2, and the fourth term would be 4 xi cube by 3, and then you put the limits. So you put the limits here, you put the limits -1 to +1 and evaluate this. So you will find that this will come out as 20 by 3. That's the exact value of this integral, but we want to do it numerically. So first thing, again we have to decide capital N number of Gauss points. So now if you see, the highest power of xi in this integrand is 2. So m is equal to 2. So when I calculate n, so n would be equal to 2 plus 1 by 2, so which would be 1 by 2, 1 by 1.5, it would be 1.5. So this is approximated to next integer. That means we would use basically two integration points. So if I use two integration points and if I carry out the integration, I will get the exact value. So now if the two minimum points needed are 2, so we need to write this I as summation I going from 1 to 2 and fi into wi. So now f is nothing but 2 plus 3, 2 plus 3 xi1 plus 4 xi1 square into w1 plus 2 plus 3 xi2 into 4 xi2 square into w2. And if you put the values, so 2 and xi1 is minus no 1 minus 1 upon root 3, so we get 3 upon root 3, and this is 4 into xi1 square. Xi1 is minus 1 upon root 3, so square would be 1 upon 3, so you get basically 4 by 3 here into 1, plus now the second term is 2 plus 3 upon root 3, and this will be again 4 by 3 into 1. So if you sum this, you will ultimately get this as 20 by 3, which is exact. So you are able to basically get the integrations accurately if you use the correct number of Gauss points. Now suppose if we use in this, for this particular function, if we just use only one Gauss point, so then we will be under integrating this. So now if we use, for this particular case, if we use n is equal to 1, of course if you use more, you can check yourself that if you use capital N equal to 3, that is 3 Gauss points, and the Gauss points and the corresponding weight factors are given over here for 3-point integration. So if we use this, then also we will get the answer would be 20 by 3. So if we use more number of points, we get basically the same value of the integral, but if we use less number of points, then we under integrate. So if we use n equal to 1, then this I would be equal to summation I going from 1 to 1 and fi into wi. And for 1-point integration, because I know the xi basically is 0, so we will have basically 2 plus 3 into xi1 plus 4 into xi1 square into w1. So you will have here 2 plus, now for 1-point integration, well, because this xi1 is different. No, this xi1 and xi2 are for 2-point integration. This xi1 is for 1-point integration. So xi1 is 0. So 3 into 0 plus 4 into 0 square into 2. So the answer would be actually 4. Whereas actual answer is 20 by 3. So this is under integrated. So we have to use the basically and of course we use more number of points, we get the exact value of the integral, but then we would be unnecessarily spending more time in evaluating the integral. So we should use basically the number of point exact number of points which are required to correctly evaluate the integral. So now this was just to show you how this Gauss quadrature numerical integration works in 1D case. Now if it is a 2D integral, so suppose now if I have integral -1 to +1, -1 to +1, and then I have a function f which is a function of xi and eta and d xi d eta. Then what we do is, because this is double integral, so this is converted into double summation. So we will have I going from 1 to n, and then another variable j going from 1 to m, and then f evaluated at xi I and eta j into wi wj. So this is how the basically double integral is performed. So if let us say n is equal to m equal to 2, and the way we decide n and m is the same thing. We look at the highest power of xi in f xi eta and highest power of eta in f xi eta, and then know that highest power plus 1 divided by 2 we take as no n and m. So suppose n and m were 2 and 2, then this integral I would have been no I equal to summation I going from basically 1 to 2, j going from 1 to 2, and f xi I eta j wi wj. So when you expand this summation, so this will be basically f evaluated at first say I equal to 1, and then xi varies from 1 to 2. So that is xi 1 comma eta 1 into w1 into w1, because I and j both are 1. Then for I equal to 1, j will be equal to 2. So we'll have f xi 1 eta 2, and then w1 w2, because I is 1 j is 2, and then I equal to 2, and then again j varies from 1 to 2. So when I equal to 2 means it would be f xi 2 eta 1 w2 w1, and then plus finally f of xi 2 eta 2 into w2 into w2. So this is how we will evaluate the 2D integral, and the same way it can be extended for actually 3D. So this is how you would be carrying out this no the integral in 2D, and the locations of these Gauss points, xi 1 xi 2 eta 1 eta 2 is same. So xi 1 would be minus 1 upon root 3, xi 2 would be for 2 point integration, xi 1 would be plus minus 1 upon root 3, xi 2 would be plus 1 upon root 3. Similarly, eta 1 would be minus 1 upon root 3, and eta 2 would be plus 1 upon root 3, and w1 would be 1, w2 would be 1 for 2 point integration. So now let's go back to the our element level governing equations for 2D heat conduction, and now we want to evaluate those integrals numerically. So how do we do that? So let's discuss that now next. So same thing, element level governing equation which we have discussed, but we want to look at the application of this Gauss quadrature numerical integration in evaluating the element level matrices. So element level, same thing I'm discussing again, element level governing equations for 2D heat conduction. So that equation you already know. So ke is ke but that is equation is ke d equal to f external plus f internal. So we know that k is integral minus 1 to plus 1, minus 1 to plus 1, and then we have k into thickness h into b transpose into b into determinant of the Jacobian j into d psi d eta. Now using Gauss quadrature numerical integration, we write this as summation I going from 1 to n, because it's a double integral, and similarly j going from 1 to say capital M, and then this kh whole thing b transpose b including determinant j. This whole thing is evaluated at xi I eta j, and then into wi wj. So this is how we will evaluate this integral using Gauss quadrature numerical integration. And I said if say n and m are equal to 2, then you would be expanding it actually like this. So now how do we choose in this case? How do we choose n and m? So I think you can think over how do we choose n and m for this case. So let me again take a simple example that if the element is a rectangle in the physical coordinate space, then for that case what would be n and m? So for a rectangular element in physical coordinate space, so we have seen that for this case the Jacobian matrix is constant, its inverse is constant. So if you look at the in B, if you look at the highest power of No, how do we decide? No, the main thing I want to discuss here is how do we decide n and m. So if you look at the highest power of xi or highest power of xi or eta in B is actually 1. Why it is 1? Because you look at for the four noded element, the shape functions n1 and n2 are basically no bilinear. So that means they have constant term, they have xi term, they have eta term, and they have xi into eta term. So the highest power of xi or eta in shape functions is basically 1. And when you differentiate no xi no n1 n1 n2 n3 n4 with respect to xi and eta, so we have seen already in the last class that no del n all the derivatives of shape functions with respect to xi have highest power of eta equal to 1, and the derivatives of all the shape function with respect to basically xi no eta have highest power of xi equal to 1. So when we look at b is nothing but no, for the rectangular element, it is simply inverse of the Jacobian, which is constant, and either del ni by del xi or del ni by del eta. So in B, highest power of xi or eta is going to be basically 1. So when we do B transpose B, so the highest power of xi or eta in B transpose into B into determinant j, because determinant j is constant. So this is going to be actually 2. So therefore you choose n will be equal to m will be equal to 2 plus 1 by 2 approximated to next integer, that is 2. So that means what you will be using, no, therefore no ke, you will be evaluating using 2 by 2 integration rule. So summation I going from 1 to 2, summation j going from 1 to 2, and then you have no this kh, and then B transpose into B into determinant of J evaluated at xi I eta j into Wi into Wj. And when you carry out the summation, so what it means is that no this kh into B transpose into B, this is evaluated at first Gauss point, that is evaluated at xi 1 eta 1 into W1 into W1, that is W1 square, and then plus no you kh B transpose into B into J, this whole thing evaluated at xi 1 eta 2 W1 W2 plus no you will have kh B transpose into B into J, whole thing evaluated at now xi 2 eta 1 W2 W1, and then plus kh B transpose into B into determinant of J, the whole thing evaluated at xi 2 eta 2 W2 into W2. So actually what it means, suppose no you want to develop a code in MATLAB to evaluate this matrix. So then what you have to do is for each Gauss point, first you take the Gauss point values of xi and eta as xi 1 and eta 1, and then get the derivatives of the shape functions at this particular point, and then multiply B transpose Bj, they are all evaluated at xi 1 eta 1, then multiply by W1, then again no calculate the shape function derivatives at these values of xi and eta, and then multiply this and add into whatever you have already done, and then you do this summation 4 times. So finally you get basically know the no element level stiffness matrix, and same thing you could do for the element level load vector also. So here I usually know in the finite element software also, when you see, you will have know the concept of number of integration points. So now in the xi eta coordinates, if I look at this no xi eta coordinate space, these points, so these are the nodes, local node number 1, 2, 3, and 4, and then you have the Gauss points. So now for the 2 by 2 integration, the Gauss points are inside the elements. One Gauss point would be here, and the coordinates of this natural coordinates of this Gauss points are minus 1 upon root 3 minus 1 upon root 3. Then the second Gauss point is here, its coordinates are minus 1 upon root 3 and plus 1 upon root 3. Then the fourth Gauss point is here, its coordinates are minus 1 upon root 3 sorry, 1 upon root 3 and minus 1 upon root 3, and then the fourth Gauss point is here, its coordinates are plus 1 upon root 3 and plus 1 upon root 3. So now these are the four Gauss points. So now you can say 1 2, let me say g1 g2 g3, they are Gauss points. So essentially this is Gauss point 1, say G1, this is Gauss point 2, this is Gauss point 3, this is Gauss point 4. So these are used for the numerical integration of the element level governing equations in the natural coordinate formulation. So all the softwares what you have, no, the all the packages, they will have subroutines, no. If you have some idea about programming either in C, MATLAB, Fortran, or any programming idea, so there is a concept of subroutines. So in the finite element packages, the softwares, commercial packages which are used for most of the industrial design problems, like if you want to analyze the whole ship or submarine or piping system, or you want to analyze the propulsion, the propeller shaft. So you will no you it won't be possible to do that manually. You have to use packages. So you will use these packages, and then the package internally what it does is does all these calculations. Of course, you don't have to, when you are using a package, you don't have to worry about all of these calculations. It does automatically. But then to use the package intelligently, you need to understand the theory behind that, how it is doing all of these. So this is how. And actually another thing is that another significance of these Gauss points is that when we do the finite element calculations, so the stresses are accurate at the Gauss points. They may not be accurate at the node points. Of course, if you use very fine mesh, very large number of elements, then the stresses would be accurate at node points as well as at the Gauss points. But if you just use optimal number of elements, which gives you the converged result for the displacements, then the stresses would only be accurate at the Gauss points. So that is at these Gauss points G1, G2, G3, G4. So yes, so once we have done this, so next is now I want to talk about this finite element formulation for the plane stress, plane strain problem. So we have already done that using three-noded triangular element formulated in known physical coordinate space. We have also done four-noded rectangular element formulated in natural coordinate space. But now we want to look at for the arbitrary quadrilateral, how we would formulate the plane stress, plane strain finite element. So basically all the steps by now is, if you are attentive with all the lectures, you would know that all the finite element basically they are exactly the same. Only thing, the sizes of the matrices and some expressions are different. Otherwise the rest of the things are actually same. So then it is straightforward as we look at all the formulations. So next I am going to discuss the, and it will not be possible to solve manually really the problems with more than one element or two elements. So that is what you can at the most do. So we have done the sum solution using triangular elements. Similarly, you would do the solutions using this. So I'm only discussing the theory over here, so that you know what are the assumptions made inside each element, and therefore you would be able to choose the appropriate element when you are using a package. So now next is four-noded isoparametric plane stress. We have seen that the plane stress, plane strain problems can be done together. Only the constitutive matrix differs. Plane is plane stress or strain slash strain finite element. So no, just now we have done for the heat conduction problem. Now the same thing we want to do for the uh, plane stress, plane strain problem. This structural mechanics problem. Again, what we are saying, similar to the heat conduction problem, that element in the physical coordinate space, that is in the xy coordinate space, it is a basically a rectangle, arbitrary rectangle. And the nodes are, these are the nodes 1, 2, these are local node numbers. The coordinates, xy coordinates are x1, y1, x2, y2, x3, y3. Same thing, no? These coordinates will come as input. So what you do when you use a package, you create the geometry, and then what you do is the discretization that you call as meshing. So when you mesh, no, the software generates the nodal coordinates and the element connectivity. So that is generated through the software. Of course, if it is your own code, then you have to give that as an input, or you have to have a subroutine which does this. So these are the coordinates, and now for the plane stress, plane strain problem, there are two displacements. Those are the primary variables, so they will be the degrees of freedom. So you will have u1e, v1e, you will have u2e, v2e, you will have u3e, v3e, the displacement along xy, and similarly for this node you will have u4e, v4e. So these will be the degrees of freedom. This element is mapped to the natural coordinate space. So that means all the approximations of the solutions we are going to do in terms of the natural coordinates xi and eta, and the nodes are the same. No, this node 1 is mapped to this node 1 over here, this node 2 is mapped to this node, this node 3 is mapped to this node, and this node 4 is mapped to this node 4 in the physical coordinate space. We have seen this for this problem, that no, the I integral functional is half integration over area of the element, and then we had no, this epsilon transpose into constitutive matrix C. This we have already derived, h epsilon h dx dy minus the potential of externally applied body forces. So area over the integration over area of the element uv transpose, and then we had body forces along x and y directions, and then because these are forces per unit volume, so we multiply by this volume, and then we have this integration over the boundary traction. So we had uv transpose, and then tnx and tny are the forces on the boundary per unit area, so you get h into ds. So this was the integral functional. And again, since the element is a 4 noded element, so you will write u the same shape functions n1, n2, n3, n4 we have defined for the heat transfer problem. The same shape functions would be used. So u would be written as I going from 1 to 4 ni ui 1 to 4, and similarly v, the displacement along y direction would be written I is equal to 1 to 4 ni into vi, actually uie and vie, because these are the nodal values. So we for the element, so we write in terms of that. And same way, the x and y coordinates are also written summation I going from 1 to 4 ni xi, and y going from again y equal to summation 1 to 4 niyi. So these interpolations are exactly the same what we have already discussed. So for this element also it is actually going to be the same. Now what we need is the interpolation matrix H and the strain displacement matrix B to write the element level governing equations. So first we write say U and V together. So see in the interpolation matrix, when we look at the degrees of freedom, so we arrange the degrees of freedom as U1E, V1E. First both the degrees of freedom for node 1, then both the degrees of freedom for node 2, then both the degrees of freedom for node 3, then both the degrees of freedom for node 4. So these are the degrees of freedom. And U is N1 U1E plus N2 U2E plus N3 U3E plus N4 U4E. So we should have N1 here 0, N2 0, N3 0, N4 and 0. V is N1 V1E plus N2 V2E plus N3 V3E plus N4 V4E. So we will have 0, N1 0, N2 0, N3 0 and N4. So this is what you can call as your strain displacement interpolation matrix. So this is H and vector of elemental degree of freedom. So this is your DE. And then you also need the strains. So strains epsilon xx, epsilon yy, and gamma xy. So these are del u by del x, del v by del y, and del u by del y plus del v by del x. These are the three strains for the plane stress problem. So again we have in between, this I I know the strain displacement matrix, and then we have the vector of elemental degrees of freedom, that is u1e, v1e, u2e, v2e, u3e, v3e, u4e, and v4e. And then del u by del x, epsilon xx, normal strain along x direction is del u by del x, and del u by del x would be no del n1 by del x into u1e plus del n2 by del x into u2e, and so on. So we will put in the first, third, fifth, and no, the seventh location the derivatives of say function n1. So we will have del n1 by del x 0, del n2 by del x 0, del n3 by del x 0, del n4 by del x 0. So this is no, with this we will define epsilon xx, that is del u by del x. Then second strain epsilon yy is del v by del y, normal strain along y direction, so that is 0. And then del n1 by del y 0, del n2 by del y 0, del n3 by del y 0, and del n4 by del y. And then when you look at this shear strain gamma xy, which is del u by del y plus del v by del x. So it involves both u and v term. The derivative of u is with respect to y, derivative of v with respect to x. So we will have del n1 by del y, del n1 by del x. So this gives you the derivative derivative of u with respect to y, and this gives you derivative of v with respect to x. Then del n2 by del y, del n2 by del x, del n3 by del y, del n3 by del x, del n4 by del y, and del n4 by del x. So this becomes your B matrix. So this is nothing but B into D. So this is your V and this is D. Only thing you would notice that H is a matrix of 2 by 8 now here, and vector of elemental degrees of freedom is 8 by 1. B will be 3 by 6 matrix, and this D is of course a 8 by 1 vector. So now if you look at the element level governing equations, so they are exactly derived in a similar manner. So I am not again going to the derivation of the element level governing equations. No, just I am going to write them. So if you look at the element level governing equation, no. So the form of the equation is same, that is Ke dE, and we have done actually this F external for the element plus F internal for the element. So where now the Ke, we are basically doing the formulation in natural coordinate space. So Ke would be equal to now integration from -1 to +1, -1 to +1, and then here you will have B transpose into C into B, and then of course you will have thickness H, and then the determinant of the Jacobian matrix into D high into d eta, and ultimately we evaluate this integral using basically the Gauss quadrature numerical integration. So this would be written as summation I going from 1 to n and j going from 1 to m, and then you have to evaluate this whole thing, that is B transpose into C into B into H into determinant of j at xi I comma eta j into wi wj, and you will do the summation over all the Gauss points. And then now similarly the F external would be equal to integration from -1 to +1, integration from -1 to +1, and that comes as H transpose FBx FBy, these body forces, H into determinant of j into d high into d eta. And basically this could be, ideally you could use a different number of Gauss points for this. So you can again write summation I going from 1 to, let us say, n dash, and j going from 1 to m dash, and then you have this H transpose into FBX, FBY, H determinant J. This whole thing evaluated at xi I eta j into Wi into Wj. And of course the F internal the is same, that you have to, after substituting the values, you have to carry out the integration over the boundary. So this integration would be integration over the boundary. So this is H transpose. Of course H is a function of xi and eta tnx tny, and then ultimately you can write ds in terms of either d xi or d eta, and then carry out this integration. So this will also be done numerically, but then you have to properly do this depending on the boundary. So here you will find that n and m will be with the same logic. The logic be used for the heat conduction problem. N and m would be actually 2, and you can use n dash is equal to m dash also equal to 2, but actually required are 1 and 1. N dash and m dash are 1, and m is equal, n and m equal to 2 and 2. So this is how the whole element formulation is done. So yeah, so with this I think I want to stop here. And if yeah, so next is I also want to, because in the packages when you analyze the practical problems, you use either 1D truss element, beam or frame element. Then in 2D, most of the time either use plane stress plane strain element or axisymmetric element, or no, the other elements are 3D solid element. So I want to discuss the next is the 3D, the axisymmetric element, and then 3D solid element and plate bending element. So three more elements to be discussed are, next is axisymmetric element, then 3D solid element, and then plate bending element, because most of your structures in submarine and ship are basically plates, stiffened plates or cells. So they are idealized using plate elements, so that also needs to be discussed. So three more elements to be discussed are, as I said, axisymmetric element, 3D solid element, and plate bending element. And then no, if time permits, I would discuss dynamics, how to know the formulate the dynamics problem. So far what we are discussing is only the statics problem. That is, we are assuming that the loads are gradually applied, so there are no the significant velocity and accelerations, the kinetic energy is negligible during the deformation of the bodies. So that is what I want to discuss. And maybe last the towards the end of the semester, half an hour I will spend showing you some problems from naval this piping system, and some from the other piping analysis, finite element analysis, how it is done using softwares. So yeah, that is where I want to stop today. So now if you have any questions and doubts, now you can ask. So are there any questions, doubts? Anybody? Okay, so then I stop here. Thank you all for your attention.